Okay, last time we formulated Eisenstein's criterion. So this is a very useful criterion that gives us sufficient conditions for a polynomial to be irreducible. So here is the most general statement. It says, let R be an integral domain and take some monic polynomial, so a polynomial with leading coefficient 1, then suppose that all of the coefficients lie in some prime ideal P but suppose that the constant C0 does not lie in the square of the ideal P. So we suppose that all the coefficients lie in some prime ideal with C0 not lying in P squared. Then, under these conditions, fx is irreducible. Okay, so before we can prove this, we just need a simple lemma. So the following lemma tells us that if we quotient a ring by a prime ideal, then we get an integral domain. And conversely, if the quotient by some ideal is an integral domain, then that ideal must be prime. So let P in a ring R be an ideal, then the quotient of R by P is an integral domain if and only if P is prime. Okay, proof. Suppose P is prime. Then we want to prove that the quotient ring is an integral domain. So suppose two elements multiply to 0 in the integral domain. So suppose A and B in R are such that their equivalence classes multiply to 0 in R over P. We would like to prove that under these conditions, either A or B have equivalence class 0. Okay, so if A times B equals 0, this is the same as saying that AB lies in P, but P is prime, so either A So if the product AB lies in P, then since P is prime, either A lies in P or B lies in P. But in the first case, this means the equivalence class of A is 0 in the quotient. And in the second case, this means the equivalence class of B is 0. So i.e. A bar equals 0 or B bar equals 0 in R over P. So we've just shown that if the product of A bar and B bar is 0, then either A bar is 0 or B bar is 0. So this, by definition, means that our quotient by P is an integral domain. Okay, now it remains to show the other direction. So suppose that the quotient ring R over P is an integral domain. We want to prove that under these circumstances P is prime. So let A, B be elements in R with the product AB lying in P. We need to prove that either A is in P or B is in P. So what we have, since AB is in P, this implies that the equivalence class of AB equals 0 in R over P. But R over P was assumed to be an integral domain, so A bar equals 0 or B bar equals 0, since we are assuming that R over P is an integral domain. But this is the same as saying that A lies in P or B lies in P. So we've just shown that if AB lies in P, then A lies in P or B lies in P, i.e. P is prime. Okay, so we've just shown that if the quotient ring by an ideal is an integral domain, then this happens if and only if the ideal is prime. And using this, we can now prove Eisenstein's criterion. Okay, so we have some monic polynomial as in the statement. And we would like to prove that it's irreducible. So suppose by contradiction that fx is reducible. I.e. that fx is a product of two non-units, so two polynomials ax and bx. Okay, so what we're assuming is that we have some prime ideal containing all the coefficients. So we have, by assumption, a prime ideal P with all coefficients in a prime ideal. Let's now look at the quotient. So consider the quotient map, the quotient homomorphism. Q this also gives us a homomorphism from the polynomial rings. Let's call it Q hat. So Q hat simply takes a polynomial, let's say a0 plus a1x plus asxn. It just reduces all the coefficients mod p. So it takes all the coefficients to a0 bar plus a1 bar x plus as bar x to the s. We just have a natural map taking all of the coefficients in R to their equivalence classes in the quotient R over P. Okay, so since we are assuming that all the coefficients of our polynomial lie in the prime ideal P, when we look at their equivalence classes in R quotiented by P, so when we look at the coefficients modulo P, then all of the coefficients other than the leading coefficient 1 get sent to 0. So since we are assuming that C0 up to Cn minus 1 lies in P, then all these coefficients have equivalence class 0 in R over P. So Q hat applied to fx is just xn. Right, so all the coefficients of fx lie in P. So if we reduce mod P, then fx becomes xn in R mod P x. Okay, so since we're assuming by way of contradiction that fx is a product of two polynomials, what we now have is x to the n, which is q hat of fx equals q hat of ax times q hat of bx. In particular, q hat ax times q hat bx, since it equals x to the n, it must lie in the ideal x in R over P x, right? Because the product is x to the n, and x to the n lies in the ideal generated by x. So we have this statement that the polynomials ax and bx, ax times bx, if I take the product and then reduce mod p, I get an element in the ideal generated by x. Okay, but x is a prime ideal in R mod px since the quotient is R mod p, which is an integral domain since p is prime. So this means that the ideal of x is a self-prime. So the ideal generated by x is prime since the quotient of the ring R mod P, the ring of polynomials or coefficients in R mod P, if I quotient that by the ideal of x, I get the ring R mod P, which is an integral domain since P is prime. And this tells us that the ideal generated by x is itself prime. So now we have a product of two elements, the reduction of ax times the reduction of bx lies in a prime ideal. Thus, q hat of ax lies in x, or q hat of bx lies in x. Without loss of generality, assume the first case. So by swapping A and B if necessary, we can assume that we're in the first case. Then, well, if you lie in the ideal generated by x, then you must be a power of x, and the power must be less than n because q hat ax times q hat bx equals x to the n. So q hat a of x, since it lies in x in the ideal generated by x, it's a power of x, and that the power must be less than n. And now we have x to the n equals q hat ax, q hat bx equals x to the m, q hat bx. And now dividing, well, cancelling by x to the n since it's an integral domain. So since P is prime, R of Px is an integral domain. So we can cancel by x to the m. Then we see that q hat bx is also a power of x. Further, we must have that n is not equal to m, or else reducing a to the x, we get x to the n. And this means, since the reduction of a to the x modulo p is x to the n, this means that ax, the original polynomial, has degree at least n, but now f of x equals ax bx, and f of x had leading coefficient x to the n. So now, since a to the x has degree at least n, and the reduction of a to the x equals x to the n, we must have that the degree of, if n were equal to m, then the degree of a to the x would have to be exactly n. It can't be greater than it because the product of it with bx only has degree n. And since its reduction modulo p is, by assumption, x to the n, if m equals n, then we must have, under the case n equals m, we would have that the degree of a to the x is n, and a to the x has leading term x to the n. Alright, because its reduction modulo p is x to the n. So this would tell us, by comparing leading coefficients, well, first of all, since the product of ax and bx it has degree n and ax has degree n, this implies that bx has degree 0, and by comparing leading coefficients, bx must be 1. This implies bx equals 1, which is a contradiction. We assumed that neither a nor b were units. So n is not equal to m. And now q hat b of x equals x to the n minus m. Since n is not equal to m, this is a positive power of x, and it lies in x. So in particular, both ax and bx modulo p lie in the ideal of x, and now taking the constant terms gives us 0. Since their powers, since we know that the reductions of ax and bx are powers of x, if I plug in 0, I just get 0. Okay, but now we are done because the constant term of f of x is f of 0, which is a of 0 times b of 0. And what we know is that modulo p, a of 0, and b of 0 are 0. So this is the same as saying that a of 0 lies in p, and likewise b of 0 lies in p, so that its reduction is 0 modulo p. And then the above equation, c naught equals a naught times b naught, implies that c naught is a product of two elements in p, lies in p squared. But this is a contradiction to the assumption that c naught doesn't lie in p squared. Okay, so that completes the proof of Eisenstein's criterion. And I warn you that the proof in the book seems to me to be incomplete. So this is the correct proof, and I think the proof in Dominant Foot is incomplete. Okay, so let me just remind you of what the statement of the criterion said. So it says if we have some monic polynomial and all of the coefficients lie in some prime ideal, but the constant term does not lie in the square root of the prime ideal, then the polynomial is irreducible. Okay, so let's look at some applications. So the first comment is that this criterion is most useful, is really typically applied in the case where the integral domain is just z. So Eisenstein's criterion is particularly useful when studying polynomials, with coefficients in Z. So we usually apply it in the case R equals Z. And just to decipher what it means, in the case R equals Z, in this case, it says that if I have some monic polynomial with integral coefficients, such that all the coefficients are divisible by some prime p, so such that there is a prime p dividing all coefficients, but with the further property that p squared does not divide the constant term. Well, but with C naught not divisible by p squared, then under these conditions fx is irreducible. So, for example, if we look at polynomial x cubed plus 14x plus 7, this is irreducible in Zx, since 7 divides all the coefficients, but 7 squared doesn't divide the first coefficient. So let's say it's irreducible by Eisenstein's criterion for the prime p equals 7. And more generally, for any prime p, well, not more generally, but for any prime p, Eisenstein's criterion applied to the prime p gives us immediately that x to the n minus p, for example, is irreducible. Okay, so to really get utility out of Eisenstein's criterion, at least in situations most useful to us, we'd actually like to work not in the ring of polynomials with integral coefficients, but in the ring of polynomials with rational coefficients. So the remark here is that we can also apply Eisenstein's criterion to show irreducibility of polynomials with rational coefficients. Okay, so let me tell you what the key theorem is, and we will not actually prove that today, but we will. So let me state what the key theorem is, and then we'll prove it next time, but we will show up, I will do lots of examples today. So the key theorem is Gauss's lemma, which tells you that if fx is an irreducible polynomial of degree at least 1 in Zx, then it's automatically irreducible in Qx. So irreducible polynomials of degree at least 1 are irreducible with integral coefficients, are still irreducible when thought of as polynomials with rational coefficients. So let fx be an irreducible polynomial in Zx of degree at least 1, so not a constant. Then it's still irreducible when thought of as an element of Qx. Okay, so here's Gauss's lemma, which is very useful. It tells us that we can use Eisenstein's criterion to decide whether some polynomial with integral coefficients is irreducible as an element of Qx. Okay, so let's make some remarks about Gauss's lemma. So the first observation is we really do need this assumption that degree is at least 1. So as far as I can tell, the book doesn't make this assumption. It leaves it out, but it's important that you assume that the polynomial is not a constant because the statement's wrong. So if you omit this assumption, so let P be a prime well, then it's not irreducible in Qx. So if P is a prime, then it's going to be irreducible in Z to the x. So if then this constant is still irreducible in Zx. However, it's a unit in Qx, so it's not irreducible. So it's a unit in rationals, obviously, if you just have a prime number. Therefore, it's a unit in Qx. Hence, not irreducible. Because by definition, an irreducible element should be a non-unit. Okay, so Gauss's lemma really should only apply to polynomials of degree at least 1. And the second remark is that the converse of Gauss's lemma is not quite true. So if something is irreducible in, so if something is reducible in Zx, it might actually become irreducible in Qx. So the element 2 to the x equals 2 times x in Zx is reducible because both 2 and x are non-units in Zx. But it's irreducible when thought of as a polynomial in Qx. So the converse to Gauss's lemma is false. Reducible polynomials in Zx can become irreducible. And in general, you need to be very careful when talking about irreducible elements in ZX to make sure that you're paying close attention to the constants. Okay. So you need to put a bit more care about when talking about irreducible polynomials in QX and you might need to do for, in ZX and you might need to do for QX. Okay, so I'm not going to prove Gauss's lemma today, we'll prove it next time, but I'd like to just give some examples of how we apply it to study fields. So some sample applications. So usually Gauss's lemma and Eisenstein's criterion are kind of combined. So let's do some applications. So x squared minus 2 in z to the x is irreducible by Eisenstein's criterion. Hence, by Gauss's lemma, it's irreducible in Qx. So then x squared minus 2 gives us the ideal generated by x squared minus 2 is maximal in the PID QX by what we proved last time. And then in particular, QX modulo x squared minus 2, let me call this K, and it's a field. And by what we proved last time, this K is a field extension of Q of degree 2. And it has a basis 1 theta over Q, where theta is the equivalence class of X in K. And it satisfies the equation theta squared minus 2 equals 0, i.e. theta squared equals 2. So we can think of theta as a square root of 2, since theta squared equals 2. And then we write a bit of notation. We write theta equals square root of 2. It's kind of just a formal notation for a square root of 2. And then we say K is a field extension of Q containing a square root of 2. Containing square root of 2. And lastly, note that since 1 and theta gives us a basis over Q, we have that K, every element in K is a linear combination of 1 and theta, or writing theta as square root of 2, I can say that K is the set A plus B root 2 for A, B rationals. And there was nothing special about the power of 2 here, so likewise, if I define K now, I look at QX modulo x cubed minus 2, then writing that I get a field extension of degree 3 of Q containing now a cube root of 2, and writing theta equals x bar as a cube root of 2, we have that K equals A plus B theta plus C theta squared is a field extension of Q containing a cube root of 2. And in this way, we can construct field extensions of Q containing roots of arbitrary polynomials. Or at least containing roots of irreducible polynomials, but you can always factor polynomial in terms of irreducibles. Okay, so next time we're going to finish the proof of Gauss's lemma, and